continents. In the program, for the abstract submission, we receive around 220 abstracts. The participants, we have about 50 students. That is a good number for now. We organize a pre-conference school that called Malcolm Muscovich School in the name of Malcolm Muscovich, who also was a very important member of the community. In the school that we organize from June 4th to 6th has a 28 student registered and 7 professors. So we were about 35 persons participating in the school. From the 50 students that registered, only 8 of them are not are decide to not participate in the conference, but only in the school. So here today we have 42 students. That is a good number also we should celebrate. And in this sense, I will ask Dr. Adolfo Andrade Seto, who is the academic secretary of the School of Science, that will deliver some words to you in the name of the director of the Institute of Science, of the School of Science, excuse me, who had some emergency that morning that could not arrive on time. So he will arrive a little bit late. So he said that anything, he will be at his office after 9:30. So is at that time he has another thing happen in the early morning. So please, thank you.
So good morning to everyone. We are very happy and proud to see many people from around over the world that is coming to our school. So we wish you very successful days in work, and we hope that your symposium will be a success. Very soon I will explain you that the School of Science that you are here now, we are 3 main departments or areas. One very important is physics, the second one is mathematics, and we that are no less important, but we are here, we are biologists. No, you will think about what biologists is mixed with mathematics and physics, but it's like this. No, we are here together. We are a very productive school. As you know, the National Autonomous University of Mexico is ranking around the 100 places in all the world. The same as physics, mathematics, and biology. Separate, we are around places 90, 87, all the stuff. And for all the academic production in the university, this school produce more or less 10% of all the papers indexed they are indexed. So we are, I think we are strong in physics, mathematics, and biology. So for us, very important that these kind of events are happening in the university and in our school, that I hope many students will attend the symposium and enrich their knowledge when what you will discuss now. So welcome all, and again, we wish you success in these days. Thank you.
Thank you, Dr. Adolfo. Now we'll introduce the Dr. Mercedes Rodriguez. She is the director of the Institute of Physics. That I think that she supports a lot that the organization of that conference, and also she is very active in the dosimetry field. So she has been participating in the conference for many years. So welcome, Dr. Mercedes Rodriguez. Well,
morning to everyone. Welcome to Mexico City. Welcome to Universidad Nacional Autónoma de México. It's for me a pleasure and an honor to preside the welcome ceremony of the 21st International Conference on Solid State Dosimetry. It's also an excellent opportunity for me to meet good old friends, all of them experts in this fascinating area of physics. As far as I understand, this is the third time that the conference takes place in Latin America, twice in Brazil, and now at UNAM in Mexico City, thanks to the hard work of Dr. Gerda Macillon, Dr. Marister Brandan, and the local organizing committee. This conference is a very important academic event that brings together national and international experts to present the latest advances in the field and discuss new challenges. The conference, coordinated by the International Solid State Dosimetry Organization, provides a forum for presentation and discussion of issues related to solid state dosimetry and a means of advancing the state of the art in this field. The conference series has been held since 1965 and has expanded its scope to cover various processes and methods available for radiation dosimetry. It's interesting to note the significant evolution of these conferences. The first ones focused on the basic principles of thermoluminescence and their applications in dosimetry, followed by the inclusion of other techniques such as optical stimulated luminescence. We cannot forget, of course, the applications in several fields, such as radiation protection, medical physics, and environmental monitoring. Around 15 years ago, the conference started to include more topics related to nanoscale dosimetry and the use of nanomaterials in radiation detection. Nowadays, we can find a focus on emerging technologies such as machine learning and artificial intelligence, as well as interdisciplinary topics relating dosimetry with other areas such as material science, physics, and biology. To conclude, I wish you the best of success in the coming days. I hope that the conference will allow you to reinforce international ties, what is more important, to increase our knowledge in the subject of this conference. Thank you so much for your attention. Thanks.
So now I will invite Dr. Thomas Kron, who is actually the chair of ISDO, the International Solid State Dosimetry Organization, to officially open the conference.
Sorry. Thank you very much, Gerda. Distinguished guests, honorable podium, and dear friends and colleagues. As the chair of the ISSDO, the International Solid State Dosimetry Organization, it gives me really great pleasure to welcome you to this conference. This is the 21st conference, and as these conferences come every 3 years, you can calculate that the conference is about just as old as I am. But unlike me, the conference has actually aged very well. It is still very young as such, and it's delightful to see all these young people here at this conference. And I think that is really one of the features of this conference. I attended the conference myself as a very young medical physicist, and I was blown away by the community of scientists who come together and try to open the field to young people, to welcome them, but to also welcome their ideas, their enthusiasm, and their engagement. You may have realized that the conference hardly has any parallel sessions, and that is really done on purpose, because that means that you're not just going to the sessions which are part of your normal work environment. So I don't need to go just to medical physics sessions in medical dosimetry, but I get to see the whole field over the next couple of days. And that is tremendously rewarding for myself. I typically find I come out of sessions where I initially don't understand the title properly,
they are the ones which I find most stimulating and exciting. And I hope you will have the same experience there and participate throughout the conference in all the different flavors of solid state dosimetry. We are obviously at the perfect location. Having a faculty, UNAM is a wonderful host for us. Combining mathematics, physics, and biology really just reflects what we will see in the next 5 days, from mathematical modeling to the physics of radiation deposition and the biological effects which radiation actually then will have. I should finish off by also pointing out that ISSDO really has the mission only to make sure that its conferences happen every 3 years. What is actually presented, putting together an exciting program, selecting venue and speaker, is really the credit of the local organizing committee. And I would like to take this opportunity to thank Gerda in particular and her team to putting together what looks like a fantastic program. So I very much look forward to the next couple of days. I really welcome you all, and I would like to open formally the conference for you all to sit back, but not relax, but enjoy and engage. Thank you.
Thank you, Thomas. So now the party begins. And we will ask Professor Makira, please. So we first of all want to thank nice introduction. We'll ask Professor Makira, please.
Well, good morning, everybody. It's my pleasure to introduce the first speaker of the conference. It's a great delight to invite to the podium a great friend of mine and a distinguished colleague, Professor Maria Esther Bradley. Maria Esther has been active in our community for many years, and I well remember being invited by her to visit UNAM centuries ago, and had such a wonderful time and learned so much from her and her colleagues. So please, Maria Esther, you come to the podium and present us with the keynote address.
First, thank you much, Professor Makira, for your kind introduction. Thank you, Gerda, for all you've done for this conference. You cannot hear. Okay. Good, thanks. There is better. Thank you. Thank you. I want to thank, before starting, I want to thank especially Gerda, who gave me total freedom in the choice of the subject for the keynote address. So after some reflection, I decided to take advantage of this unique opportunity to present you what has been our dosimetry project in this university over many years now. Of course, we all know, okay, I didn't read the title, that's a big mistake. I will talk about our studies on the TL response of a couple of TLDs that is depending on LET. Things will become much more clear later. We all know what thermoluminescence is, and I want to show that photograph. That is, I will call it a TLD tutti frutti that has been prepared by Eduardo Lopez, one of the members of our group. Where is Lalo? He hasn't arrived yet. And he mixes 3 or 4 types of dosimeters, gives them a couple of grays, and then puts them on a hot plate. That while the students visit our laboratory in our open days. This is just our own image of how thermoluminescence can be fun and interesting. Now, how did I get into directing a project that had to do with thermoluminescence and LET? And here comes a few historical details. I studied my graduate degrees at the University of Wisconsin-Madison, and as we may know, the thermoluminescence of lithium fluoride was discovered and first studied by a chemist called Farrington Daniels, who worked in Madison in the 40s, last century. Farrington Daniels worked with ground lithium fluoride and with hope of producing a detector based on thermoluminescence that will be of interest to medical results. It is said that he even used his lithium fluoride powder to evaluate radiation during the nuclear tests in New Mexico. In year 58, John Cameron arrives to the University of Wisconsin with a joint appointment in physics and radiology departments. He's a young nuclear physicist who is disappointed of the opportunities that nuclear physics offers and thinks that a much more interesting path for him and for the rest of the people will be to develop projects around medical physics. John learns about Farrington Daniels' results and offers to help. Farrington Daniels he did not have a very successful results with the lithium fluoride because of many technical details that I don't have time to explain, but I really, someone who wants to learn about those beginnings, I invite you to look at these history interviews in the NPM webpage. And in 1992, John was interviewed 3 times, and he tells details of the beginning of the thermoluminescence work in Madison. So John, in order to help Farrington Daniels, he understands that he had instrumentation problems that he helps to solve. And then he contacts Parrington Daniels with Harshaw Company, and they work together in order to optimize the doping of lithium fluoride that at the time was not with titanium magnesium as we know now, thinking on TLD 100. In the next, well, more than 10 years later, another young nuclear physicist comes to Wisconsin, now recruited by John Cameron with a clear idea of strengthening medical physics. And that's Paul De Luca, who is at UW since 1971. And these two guys and Herb Atix were the ones that created the medical physics department and created the graduate program that comes with it. I was a student in the physics department, not knowing that medical physics existed at the time. And I took a course. I took a radiology course called it was health physics, but given by the radiology department with Paul. And many years, all the decades that you can imagine later, I still remember one of the lab sessions in the health physics course. The lab session was called thermoluminescence dosimetry. Of course, we were in Madison, and we were given TLD 100 chips to expose them to gamma rays from a cobalt 60 unit. I did the measurements and I got a glow curve in a Harshaw 2000 set of equipments, and I got a typical glow curve for gamma rays. So is this first peak. When the practice had finished, Paul showed a different glow curve, very similar to this. I couldn't find the original in my papers. Very similar, it showed two peaks. And I remember very clearly that he explained to us that the glow curve of TLD 100 could tell us about the quality, the quality of the radiation field, and that those and that this glow curve came from a mixed field of neutrons and gammas, and that peak A, let's say, came from the gammas, and peak B came from the neutrons. That was fixed because when I thought a little bit about the whole issue, I thought that that didn't fit with the first image he had given us for how thermoluminescence arose. I could not imagine how an electron knew if he came from gammas or neutrons before going to the conduction band and then having to choose in which thermoluminescent trap to form. I didn't ask for an explanation at the moment. And simply, I did not forget this feature of TLD 100 glow curves. So that was my first encounter with thermoluminescence, and with LET, it was right at, of course, immersed in many of the classes of the health physics course. So I just want to fix some ideas and define LET, because that has been the physical parameter that has guided our research project. When one talks about LET, the best is to start talking about stopping power. That is much simpler to understand. So the stopping power of a medium for charged particles of a given type and energy is simply the ratio of delta E over delta L, where delta E is the mean energy lost when going through a distance delta L. Since these energy losses depend strongly on the density, we divide by the density, and then one starts thinking on where is this energy going to? What is the medium doing with this energy? And we can separate into large groups, one that's now called electronic, in the past it was called collision, the electronic stopping power that takes care of the losses that will go into ionization and excitation. That is, that energy will get close to the track, except for those electrons that may have gotten a lot of energy and will run far away. The second group are the energies that will end up in bremsstrahlung production that will also go away. For ions, there is essentially, there is very little bremsstrahlung production, so we can just have one term. Now, LET. LET is worried about the spatial distribution of this energy already absorbed in the medium. So we will take the stopping power already defined, but only the electronic part, and we will eliminate the bremsstrahlung because it will not be locally deposited. And to this electronic stopping power, we'll put a restriction and we'll say we will not consider those transfers that are larger than a limit or a restriction energy called delta. So we define L sub delta, a restricted stopping power in this way, and derive from the stopping power definition and calculations. The units are adjusted to radiobiological needs of the 60s. So in general, one talks about in terms of kV per micron. And since stopping power is only defined for charged particles, and non-charged particles like gamma rays are very important in all this story, for them, one can define a stopping power considering the secondary charged particle spectrum. I think this drawing is probably the best way to show what I've tried to explain. Here we have electrons in water, here we have the electron energy, and here the energy losses per unit length. So we can think that this top curve is the stopping power. This fast rising section comes from the bremsstrahlung. In order to think on LET, we do not include the bremsstrahlung, so we are left just with the electronic stopping power. And once we apply the restrictions in deltas, and here we have 3 deltas, we have 3 possible LETs, if we want to call them that way. Now, LET is extremely relevant in radiobiology. We have here the classical image of Barentzen's measurement in year, this publication is 68, where he exposed, he and his collaborators exposed cell cultures to ion beams, different ion beams that get represented on this axis by their LET value, just one number for the complete beam. And then what he's showing here is how efficient these different beams are in producing a given biological effect. If we look, for instance, to curve number 3 and read that a radiobiological effectiveness of near 3, that means that one needs 3 times less dose if it's imparted by these high LET particles in order to achieve the same biological effect. One has classified particles according if their LET value, and we have low LET and high LET particles. The explanation for this, these were mammalian cells. These particular curves is shown in this image that shows DNA. And here is this is a high LET track. And we see how easy it is for this track, due to the spatial pattern of energy deposition, to break DNA, the two strands of DNA in neighboring bases, and then to cause irreversible damage. So there is interest in knowing LET and learning. Not only biological systems are dependent on LET, also many physical and chemical do too. So here I am in Mexico in 1995 as a young scientist and working as a nuclear physicist in an experimental physics department. The institute decides to acquire a new accelerator, a low energy, 3 megavolts on the terminal, a tandem called of the style Pelletron. This machine gets inaugurated, is bought brand new in 1995, and we are invited to propose projects. And then I remember that class with Paul, and I remember that there was something interesting with dosimeters and LET, and here I will have ions with large LET, large values of LET, but certainly a large variety. So I present a project that gets included in the list of projects for the Pelletron, and we start. What we had, the project was to study the TL response to densely ionizing radiation, at that moment using ions. Later, we have turned into low energy photons. As a radiation facility, in that moment, we also have the Pelletron. Later, we got this, we expanded, as I will tell the rest of the story. At TL dosimetry lab, I had never been interested in thermoluminescence dosimetry. As for my PhD thesis was associated to LET, but not to TL. So we had the old Harshov 2000 readers, and the Institute very generously bought a Harshov 3500 that we still have. It works well, I would say, given the age, and now we have a second one. As for ovens, we got whatever ovens we found around. One of these was given by John Cameron, who sent it from his lab in Madison. And the most important, well, we will need a radiation facility, a TL lab, and then we will need some interpretation to the results. And there we had people who did excellent Monte Carlo simulations and calculations for any physical problem. They joined us. The most important has been the great student support. This is a group, a photo of our group just before COVID in the winter of 2020. So how are we going to use the Pelletron? The Pelletron is there, and those who were at the school last week, some of you visited the Pelletron and visited the scattering chamber. You looked it from the outside. Of course, now this is not inside the chamber anymore, now that the project finished. But this was my idea. Low energy ions is a 3 megavolt machine. Low energy ions on a gold foil that's below the Coulomb barrier. So there are no reactions. Everything is elastic scattering. And elastic scattering is described by the Rutherford cross-section that is analytical and very easy to calculate. So we knew how the scattered particles, the scattered ions will distribute in space. And if we here would put our TLDs, as you see in the photograph, we will get at each different position a different fluence that we will know because it was calculated from Rutherford. Here we had in the back a sort of a monitor, a surface barrier solid state detector. Here is the photograph, the target, the TLDs. There is a blue line, that's a radiochromic film strip that we put behind the dosimeters so that afterwards we will check that everything had gone well. Of course, the blue line follows the Rutherford cross-section. Which were the challenges of the project? Here, this is a cartoon of an ion track. It's coming from this side at high energy. It loses energy, and as it loses energy, its LT increases. I show the electron curve much too fast. Here we have proton stopping power over a very wide energy range. This is 100 kV, and this must be close to, I don't know, 100 MeV probably. And we see that LT depends on the inverse of the velocity square multiplied by Z of the particle square. So we will have these ions in the chamber, and we'll put our TLDs, and the ions, since they were low energy, they will stop very rapidly. We will be talking about densely ionizing particles, very short tracks for the helium ions, less than 50 microns. So everything that interested us was happening at the surface, at the entrance surface. And that meant that we had to be extremely careful with the handling of the dosimeters. Since then until today, we have strict rules in the lab so that these experiments could be well done. We have clean and controlled handling of the TLDs. The ovens, of course, we have never put a pizza in the oven. That will need to be expelled from Paradise immediately. If there was a time where these TLD 100 studies were done, that the oven was also used for TLD 100 and a different oven for the other types, then of course we don't touch them with our hands. We wear gloves, tweezers. The ambient conditions are controlled, so the lab is dark and cold, but funny. And then for the glow curves that we will be getting, very rigid the convolution procedures. We think we have done all that well. We are waiting for Steve McKeever's talk later today on how one should be doing the convolution procedures of glow curves. And then this, from my first memories, I knew that each peak had to be a different entity or a different beast, so that our analysis was always done peak by peak. That meant that before we had to do a careful deconvolution. In terms of interpretation, those that were the current theoretical models, when we started, track structure, track interaction models were implemented in Monte Carlo platforms by the members of our group that knew how to do this. And here you have a beautiful glow curve of TLD 100 taken at the pelletron. These are 7.5 MeV helium-4 ions, very similar also in energy to what an alpha particle from a radioactive source will show. And maybe here we have the two groups that I remembered. A low temperature one, that is the dosimetric peak 5 and his neighbors. And here we have the high temperature peaks that you generally don't see when you irradiate with gammas, but you see so strongly expressed when you use high LET particles. And I will show numbers later. These ions had an LET of 66. summarizing our results, because I had to move very fast, I will only show you these relative efficiency results that we obtained for, well, five ions out of peloton. We used all the beams that were available, you would imagine, and we will use up to the highest energies that we could reach with the accelerator. And here we have peak 5 relative efficiency relative to cobalt-60 gamma rays, peak by peak. This is peak 5 as a function of LET. And you can see here these points falling down are at the other side of the Bragg peak. And this wonderful display, well, I have to acknowledge mostly the theoretical efficiency interpretations of the curves that you see were done by Olga Avila, who was a part of a group. Now she works at the National Institute of Nuclear Research. This type of beautiful work, beautiful displays, are the endpoint of a very complex simulation of what happens with heavy ion tracks on lithium fluoride. Here is the probability of occupancy of defects for 2 neighboring tracks, and these simulations done by Mercedes Rodriguez, my director at this moment, and who just inaugurated the conference. She got the ISTO award in the Athens conference with this work, where this beautiful image was published.